So it's a great pleasure to be here in Birmingham. A long time ago I was here, but it's about time I came back. Thank you, Mike, for this nice, extensive presentation. And then I tell you a story. Bob Woodward was known for giving very long lectures. And when he presented the first time at Harvard, the total synthesis of vitamin B12, he was introduced by David Dolphin. Some of you may know David Dolphin, who spoke for 45 minutes for the introduction. So Woodward stood up and said, "People tell me I'm giving very long lectures. Now I know why." So I'm happy to have 5 of my former co-workers here in the room. One I haven't seen for quite some time. And it's a pleasure to be around, to see them, and to tell you a little bit about what has been going on. There will be selections from earlier work, which some of you know, but maybe a number of you don't know. And I know, in science, your work is scientific work, and this is linked necessarily to a person. So many of the young people don't know some of the important people in the past. Then wait a minute, a test. Who of you knows Robert Burns Woodward? Lift your hand. Not so many, huh? Which is, in fact, in some ways, should make scientists modest. They have a contribution. He had enormous contributions. And we just contribute to science. Another test. Who knows Albert Eschenmoser? You don't count. You don't count. You see, he's also a giant in chemistry. And I could cite many others. Anyway, this was just a note. Okay, so let me tell you about some of the things that we're doing. And here is, of course, Norman Haworth, and he got the Nobel Prize, as I have seen present earlier. And my talk is about perspectives in chemistry, and we will move from supramolecular to what we are doing now, which is what one may call adaptive chemistry. We'll see why. For this, let's start, for those who are not exactly in the picture. As you know, molecular chemistry, that is the art and science chemists have invented to make complicated structures by linking together atoms. Again, incidentally, my lecture will be longer than usual because I will make sort of spin-offs. Over there, you have the periodic table of the elements. That's the playground of chemists. Chemists use these bricks, and these are the bricks of the universe. Since tomorrow you cannot be in my general lecture, I will make a bit of those side steps. This table, it is today, this year, the 150th anniversary of Mendeleev's publication in 1869 of the first presentation of what has to become the periodic table. And in our universe, visible matter, and we are part of visible matter, is built on that everywhere in the universe, from the planet Earth to the end of the universe. You realize what that is? You are sitting in this room, and you know what visible matter is made of everywhere. Isn't that fantastic? Chemistry has brought that. No, I'm not joking. I'm always very impressed when I see that we know what visible matter is made of. Any organism will be made of that, anywhere. Okay, now let's continue. So the art and science of playing with this is a playground of chemistry, and beyond this molecular chemistry, where you link atoms to the molecules, you can then develop a chemistry which deals with how molecules get together, what are larger assemblies which lie beyond the molecular chemistry, and which uses weaker interactions, what are called non-covalent interactions. Of course, a physicist would tell you, oh, that's the same, or that's the Schrödinger equation. That's right, but it's very difficult to solve the Schrödinger equation in your brain. In fact, nobody is able to do it. So you have to use sort of the big sections in science, in chemistry, and from molecular you go to supramolecular. Without molecular, there is no supramolecular. So we all stand on this. But supramolecular is a step which is beyond the molecular chemistry. And the three processes which were studied for many years, and the basis is how the molecules recognize each other. A process which is very important, without which there is no life. As you're sitting here, the molecules in your body, they do what they do because they recognize each other. Otherwise, you don't exist. They have to find out what the partner is, how it operates, where it operates, at what rate it operates, and so on. Then another aspect of that is reactivity, how the molecules react with one another, like enzymes, for instance, I've taken on the substrate, and transport processes, how do you bring something through a barrier, like a membrane, artificial or natural. And molecular recognition has been the first step, the first very important step, where this question of specificity in molecular interactions and specificity in biological processes comes in. Now the step beyond this molecular recognition, where you test, and chemists can do that, that's another power of chemistry. You can pre-organize matter to demonstrate a given property, and to demonstrate recognition, one can, and did over the years, make chemical objects which are able to bind to other ones. Of course, enzymes do it, but you can do it in a lab with entities which are totally non-natural, and I always make a strong point on saying that chemistry goes beyond nature. Chemistry makes things which don't exist yet. And that is quite a fantastic feature also. It's like art. In art, you make things which don't exist yet. And this you can do with chemistry. So, beyond this pre-organization of matter comes the next step in complexity. Can matter self-organize, generate complex objects on the basis of how the pieces are built? And this is called self-organization, which can be at equilibrium, thermodynamically controlled, an equilibrium system, or out of equilibrium. That is much more complicated. So most of the work, what I will describe, there are some cases of non-equilibrium, but most is equilibrium, self-organization. But of course, the out of equilibrium is much more complex and very important because we are out of equilibrium. Our equilibrium is CO2, water, ammonia, phosphate, calcium phosphate, and so on. Not very funny, but that's how we will end up anyway, all of us. So self-organization is for me also the major property of our universe. That's why we exist. Our universe, I'm a little bit adding things which I'm going to tell tomorrow, but since you cannot be there tomorrow in my general public lecture, and people a more broad audience, self-organization drives our universe. That's why we exist. Our universe has a structure such that it can lead to systems which result from the self-organization of the pieces. That's why we are around. And this then can be transformed or can be tested in the laboratory by trying to set up systems where molecular information tries a system to generate complex entities in a controlled way. Because you want to put in the information needed to generate a given entity. And I will start very briefly to give you some indication about one category of those self-organizing systems, which is a sort of a programming of what molecules do when they get together and build up a larger structure. By design, I mean by that you try to figure out how to build these building blocks so that they will generate in a controlled way the outcome. Let's take one example, and I think in this, of course, in this department, especially my canon, has been working on trying to use what is called metallo-supramolecular architectures. That means supramolecular architectures built on using metals, and what is done there is to take molecules, to design molecules which can bind metal ions, and then choosing the right structure for the molecule and the right structure, the right coordination for the metal ion to build up a given entity. So the connectors are metal cations and the ligands are the building blocks to start. So the metal ion reads the structural information. I like to use the language of information because chemical systems are all informed. All molecules, they have an information. And this information is read out by the connections between them. And this is something which is, of course, obvious in biology. That's like DNA functions, and the DNA, the genome, it's a strand of molecules, of letters, 4 letters, which then are read out by supramolecular interactions. So, you have a structure information, the ligand molecules. The coordination can be called the little reading algorithm, the way you read it. The middle ion can have a coordination which is linear, square planar, or octahedral, or tetrahedral, and so on. So that can be called the information, the reading algorithm. And of course, you can also try to use this for, I'll come back to that, nanoscience and nanotechnology. So you want to spontaneously generate the architectures, but you want to control it. And each step in this organization, new properties can appear. I have no time to get into all that, but just as it gets more complex, new properties can come about. So initially, the first time we sort of thought about introducing this idea of generating on design specific structures was to make double helices, because DNA is one of those big things of biology. The genome, double helix. Question, can you make double helices which have nothing to do, absolutely nothing, except that they are double helices with components which are not the ones of DNA? And so the idea there, this was now quite some time ago, was to replace the strands of the genome by totally different ones, where you have here, this would be the analog of a trinucleotide in DNA, bipyridine, bipyridine, nothing to do with DNA. And you link them together not by making hydrogen bonds like between base pairing, but by 3 copper-1 ions. And copper-1 have a tetrahedral geometry, so you must get, I haven't time to get into details, you must get a double helix from that. You can also make triple helices, and so this was just a way to show you that by design, you spontaneously generate those. You don't have to do anything else and design them well, of course. Now, another set of structures of interest were those ones where you have a molecule which is rigid, and it has slots here where you can introduce metal ions here. Depending on how you design those things, these are the binding sites of the metal ions. Depending on how you design them, you have to choose the right metal ion, and then they will assemble in such a way so that each crossover of the ligand molecule, you have a metal ion holding the thing together. And this is like one example where you have to synthesize, of course, those things, and then you have to use the right metal ion. Octahedral coordination. Just a point here to make you understand what's going on. Octahedral is twice 3 points in 2 perpendicular planes. This one, okay? That's what it is. That's an octahedral. So if you use a unit which has 1, 2, 3 binding sites and use an octahedral connector, it automatically has to do this. And that is why you get this type of structures. The simplest one, the 2x2 grids, this was studied very extensively. Here is just one example where you automatically obtain those objects. Of course, because they are multifunctional, multi-ligand, multi-nuclear, multi-metallic, with metal ions, you get new properties which are, for instance, chemical, photochemical, magnetic, and so on. This is just a very, very, very small selection of the zoo of all these structures which have been made. This is a grid where 6 ligand molecules are held together by 9 silver ions, and this again is made spontaneously. That's another one, which is somewhat more complex because there are 2 types of ligands. There are flat molecules in blue, and there are linear molecules in red, and they're held together by 12 copper. So that thing is just an illustration that 12 entities, they go together and generate one entity at the end. And these are just other nice looking ones because, okay, I think it's nice to see the very convex one. In fact, I will come back to this one in a moment. Of course, very complex models, architectures have been generated by many people, much more complex than this one. For instance, Fraser Stoddart, who is somebody who has been in this department. Fraser has done very complex, has generated very complex architectures by the same principles, just using the right way, the right structures for the Lehn, and then the correct midlines to assemble everything. So now the question is, and this is just one example of how your programming can be made even more complicated. Multi-code synchronization, more than one code. Let's go. Look at this molecule. This molecule has, at the ends here, 2 units. Sorry, let's go to the middle first. In the middle, a unit which is known to form a grid. Okay? And at the ends, pieces at each end, which are supposed to form a double helix. So this is a very frustrated molecule. It doesn't know what to do. So what can you do with it? You can then use what I called algorithms middle coordination, where you can have hexa coordination, tetra coordination, and also penta coordination, 5. And then you can try to process the information present in this strand to generate specific architectures. Let's do it first by using 4, and here I'll use a hexagon because there are 6 sides for octahedral coordination, hexa coordination, and the square for 4, tetrahedral, just to simplify. If you take 4 octahedral, 8 tetrahedral, of course you will immediately say, okay, the guy in the middle will give a grid. That's what he does, and he does this. In this case, you have a grid in the middle, and each corner has a double helix. That is also generated automatically. But more interesting is the following one. Take 5 coordination, 8 of those, and 4 of tetra coordination. How do you make 5 with that? You make 5, at least you can on paper, think that you can make 5 by using 2 here and 3 here. 2 plus 3, 5. So what is the result of that? In other words, if something sensible comes out of it, one piece with 2 binding sides, 2 nitrogens, has to in some way to connect through the pentacoordinated middle ion with the 3, which is the center. And the result is this. So this, you would not be able to get it by stepwise synthesis. You have to design the system, and people don't believe you if you don't have a crystal structure. I have one, I will show you. So, I have one. So what happens here is that, you see, this is a strand, and this is the end of one here, bound to the center of another one. And this is the one which results from this and that, giving here a double helix. So you have a double helix, which sort of wraps around, is entangled, and generates a circular type of unit, which is what you see here. Now, the first one here, the 2 subroutines, subprograms are linearly combined, because each one does what it's supposed to do. The middle grid, the end makes double helices. But the one on the right here is the one where you have to entangle things so that you can generate that object, and that's what you obtain. Here is the crystal structure of this one. We don't have the crystal structure of this one because it doesn't crystallize well, as you know, that's always a problem, get crystals. But all the properties are in favor. And anyway, the interesting one is this one. This one, nobody would have believed you that you get it. And as I said, Fraser Stoddart, Peter Stein, Jean-Pierre Sauvage, and many others around the world have done even more complex entities than that. But this one is an interesting one because it has really 2 programs which are combined. That's the other one. Okay, so the most important out of this is not that we get, okay, it's an interesting object we get, but the most important is the following, that the molecular information in one strand can generate 2 different objects at the end. You have a single program which has several, let's say in this case, 2 outputs. In biology, 1 code, 1 protein. But you can imagine that the way you read the program can influence the output. It's not something, it's like the generate information. The information is present, but the reading process can generate different things from that information. That can be quite interesting, perhaps also for biology. Now, this has some importance in that now I sort of just generalized for nanoscience and nanotechnology, being able to program a system in such a way that it will generate even architectures. And you will think of, if you want to expand it, to think of the fact that you can make devices by stepwise assembly, where the first assembly step prepares the stage for the second one, the third one, and so on. In fact, we have done a little bit with 2 steps, but of course 2 steps is not enough. But one can say that in nanoscience and nanotechnology, maybe it's not an alternative, but it's certainly a complement, a possible complement to the generation of devices for electronics and nanoscience and nanotechnology. And of course, in some way, this stepping from fabrication to self-fabrication is ultimate fabrication. You design the system, you let it go. In fact, it's the brain, our brain is for. We don't make our brain, it is self-organized. Now, this was just an introduction, because now comes the main point. I don't want to look at my watch. And by design, you put in information, you have programmed the system, you let it go. But the next step is to let the system do the job. Let the system, which is able to generate functional, molecular, and supramolecular entities, to do the selection. In other words, from a diversity of pieces, the system may just pick up the bricks it needs to make itself. That's another step in complexity, because also in biological systems, the molecules, they know what to pick up from the environment to function. And that would be the same thing. In addition, you need dynamics. I mean by that you cannot just count on the fact that the first collision will be the correct one thermodynamically. So you have to have the possibility to disrupt, reassociate, and change in the process the structure, the components, and so on. And so it must be a dynamic system. This leads to what we call, it's a bit complicated name, but it really describes what it is. We will see in a moment. Constitutional dynamic system, dynamic chemistry. I don't explain it, it will come. And because you can exchange your groups, you can also hope that if the conditions change, you will be able to adapt your system, and that is opening towards adaptive chemistry. So that is just a program for the next rest of the talk. So how did we come to that? And you see, often that's also not for the seniors here, but for the young people. When you do experiments, sometimes they want to tell you much more than what you were looking for. So don't miss the boat, don't miss the train when there's a train there. And usually I could have many examples where people have missed the boat for very important discoveries, which were then put back by 40 years or so. So, the first hint was the following. And some of my co-workers here will recognize the names. We had made these double helices, okay? These are the components of making the double helix, the helices. We had made triple helices. These are the components which make the triple helix. Then the question is, what happens if you mix them? Of course, for a chemist, that's horrible. You spend an enormous amount of time to try to have pure compounds. And suddenly comes a guy and tells you, let's mix them. But he tells you something which is important. Is the system well enough programmed to generate what you want it to generate, despite the fact that it's not pure anymore? And when you mix this together, you get exactly what you expected. You get the good double helix, you get the good triple helix. You say, so what? We knew. Yeah, but we knew when they were separated. And now we know what happens when they are mixed. So that's a sort of a self-recognition, or we can call it a homo self-sorting process, where the pieces recognize each other, and the thermodynamics drive it to generate the correct object. That was the first step. Roland Kramer, we talked about him, he was in the lab at that time, and EOC also. Now, the other thing was when Bernie Hassendorf was working in the lab, and they knew him too. He used this type of strand with an iron salt to bind it. And he found that when he used iron chloride, he got this very nice molecule, which had, like a flower, 5 irons and a chloride in the middle. So first of all, at this stage, you could say, all right, it's nice, we obtained what we wanted. We want to have a sort of circular, like in plasmids, a circular DNA, a circular helicate, and say, okay, we have it, and we continue. But then again, this is a case where you have to think a bit further, and you say, why do we get a pentagon? Because these building stones, they could lead to pentagon, hexagon, octagon, square. That when you have bricks, you can build any type of house with the same type of bricks if you combine them differently. So the question was, we knew that the chloride in the middle was bound very, very strongly. So the obvious question you can ask is, maybe it's a chloride which drives the system to make a pentagon, because it feels very well in the middle. That means electrostatics drives the system. And that is the crystal structure of this. And so if you change now, and this again, what chemistry can do, you test your system, you replace chloride by something else, for instance sulfate, and you get a hexagon. And when this is a hexagon, you add chloride, you go back to the pentagon. So that indicated what? That we have what you may call a dynamic set of potentially interconverting entities, which is you can call it a dynamic library of circular helicates. And it's an adaptive process also. Depending on what anion is present, you have something else coming out. So that opened this to this idea of adaptive chemistry as the first steps. So then you realize that you have always that in your hands. You know, this is also something else, something you take for granted. It's obvious. Then you have to think a bit more and say, maybe it's obvious, but it's not exploited. And this is also often the case where some things are obvious and you sort of forget about because they're obvious. But you have to think about what you can do with this obvious case. And here the case is that supramolecular chemistry was for everybody practicing it a dynamic chemistry where the pieces can fall apart and recombine because the binding between the pieces is not very strong. It's weakish compared to a covalent bond. And so, it is supramolecular chemistry, it's a dynamic chemistry because of the lability of these interactions, which allow changes in the constitution of the object. This we call a dynamic non-covalent chemistry. And then another step where you break the laws, as we will discuss tomorrow. Chemists and molecular chemists at the start are trained to make stable molecules. And when the molecule is not stable, you put it in the fridge to cool it down, so to prevent it from doing something else. But then you can take the opposite point of view and say, what happens if you intentionally introduce reversibility in the bonding? Some people say that's stupid, you will not be stable. But maybe there are new things there which don't exist in static molecules. You can do that by introducing into the molecules bonds which are reversible. We can break apart, reform by reactions, which are well-known reactions. And this leads then to a dynamic covalent chemistry. And if you want to put both under the same heading, you can call that this constitutional dynamic chemistry. It simply means that the chemical object you look at, be it molecular or be it supramolecular, has the ability to change its constitution by dissociation, reassociation, and in the process can change even the components it is made of. This makes possible adaptation because you have the possibility to change depending on the conditions. And this leads to adaptive chemistry. Now, at this point, I would have to say that this chemistry has been developed, dynamic covalent chemistry, not the rest, but dynamic covalent chemistry has been developed independently by Jeremy Sanders and his group in Cambridge and by us in Strasbourg, using different types of reversible reactions, but with the same idea to try to make molecules which can assemble their building blocks. Now, what is this good for? This constitutional dynamic chemistry. Furthermore, you build up, you generate constitutional dynamic libraries. Now, that's a very nice name for designating a mess, a mixture, a horrible mixture. Not so horrible, but when I did my PhD, and maybe some here too, with a mixture like that, you put it in the sink, you cannot analyze it. And thanks to the modern, very, very highly performing technologies for studying complex mixtures, NMR, mass spec, and mostly those two, you can now analyze these. Now, this generates then dynamic diversity, and of course can lead to recognition processes which then induce a selection. It can be of interest for biologically active substances, making them, maybe dynamic nanodevices, and materials, dynamic materials. I will discuss the biological ones and the materials, not the one in the middle. Now, interesting here is also the fact that because you can recombine, this generates diversities, combinatorics. But recognition is the process which drives the system. So you have both information to the recognition process, and you have diversity going for the recombination, and this together, what will it do? Let me give you an example with the biologically active substances. First of all, what kind of reactions can you use? You can use one of the emblematic reactions of organic chemistry, which is to condense an amine with a carbonyl group here, making an imine, or let's say a CN double bond. And there are different types of CN double bonds. As you know, there are amines, there are hydrozones, there are ether hydrozones, there are oxenes, and so on. CN double bonds. And that is the one we were concentrating on. So, let's look at imine formation. Then, you can apply what Emil Fischer would have called the lock and key principle. Emil Fischer, again, some of you know that of his existence. Emil Fischer was the person who in 1894, 9 years ago, proposed that for an enzyme to act on its substrate, they have to fit together like a lock and a key. That's the lock and key image which Emil Fischer introduced end of the 19th century. At that time, we didn't call it molecular recognition because it was a time of mechanics, not a time of informatics. But nowadays, we can call this lock and key principle as sort of fitting together with the information present in the objects. But so let's go back to the lock and key. And then you can imagine ways of finding biologically active substances. The one which would be the one preferred one for all pharmaceutical companies is to make one key for the lock, the correct one which fits. Okay, that looks good on the basis of molecular recognition and so on, understanding the processes. But if you don't isolate the lock, if you don't look at it, you don't know how to build the key. So it may be very interesting in terms of basic knowledge on molecular recognition, but it may be not possible because you cannot find until you can, let's say, crystallize the lock, get a crystal structure, and then build the key. Then come the people, and here I simplify a lot, in most, I guess all, big pharma companies now, they say, okay, these guys who want to understand, that's fine, but it will take a long time. So what we do, we will generate many keys, and just try them all, by fast robotics, by fast screening, high throughput screening, and eventually, if we are lucky, one of them will be more or less active. That means if the first 100,000 don't work, you make another 100,000, and so on and so on and so on. And once you have a lead, medicinal chemists will synthesize around that and make it better and better. But that is not much fun, because you just count on chance to find it. Then you can think of combining the two by making dynamic copulatory chemistry, which is to make fragments of keys, not keys themselves. How? It will become clear with this. These are components of different sizes and shapes and nature of structures, which have a small piece here, a small unit here, which is a reversible functional group, which can make reversible reactions. The mixture of those leads to this. This leads to a dynamic combinatorial set of constituents. So these components give dynamic constituents which represent all the combinations accessible. In other words, they don't even need to be present, but you have access to the whole space of all combinations. So you say, okay, so what? What's the next step? The next step is you take your telephone and you call out Monsieur Le Chatelier. Who knows Monsieur Le Chatelier? The law of mass action. That's a thermodynamic rule, which is that if you introduce a receptor, the one unit which can bind one of those constituents, it will select automatically, thermodynamically driven, the one which fits best. Out of the mixture, we select the best one. And this then means that the recognition is doing the driving. The log assembles its key. And this is a way, in principle, where if the receptor is some kind of a protein, you don't need to know its structure, it will automatically assemble what binds best. So we have nevertheless to at least demonstrate that have a proof of principle. We did that by using an enzyme, carbonic anhydrase, which converts CO2 and water and interconverts CO2 and water with carbonic acid. And this is the active site, very simplified of course, of the enzyme, and many inhibitors have been studied for that. So it's better to start when you want to make a proof of principle with something we know the answer, to see if it fits. And this active site has a zinc and has a hydrophobic wall. And this is one of the most potent binder inhibitors of carbonic anhydrase, where this sulfonamide binds to the zinc in the active site, and this benzylamine group binds to the hydrophobic wall with a KD of 1 nanomole, very strong, 10^9 association constant. So you say, okay, but nothing is really here reversible. So what can we do? In fact, you can see the following. We can assume that this interaction and this interaction are dominant, and replacing the amide by an imine, although you perfectly realize that it has not the same intermolecular interactions, but maybe it's a minor perturbation on the outcome. So, okay, let's try. So the following was tried. Of course, we didn't go for a very big library at the beginning. 4 amines, 3 aldehydes. You make sure, you know the answer, so you make sure that one of the amines is benzylamine. You make sure that one of the aldehydes has a sulfonamide here. You mix them, 3 times 4 is 12. You can generate 12 combinations. One of these 12 combinations, this one here, is the closest of all of them to the very strong inhibitor. So, the test is the following. You mix the whole thing in absence of carbonic anhydrase, and then you add carbonic anhydrase. Looking at just 2 of the constituents in this set of 12, this one and this one, which share this sulfonamide, but where the other group is different, in absence of carbonic anhydrase, these 2 have about the same intensity in the chromatogram, high pressure liquid chromatogram. And then you add carbonic anhydrase, and you have this. So this one is strongly enhanced with respect to this one, which does indeed show that carbonic anhydrase has amplified the one which binds best. And that is then a way to amplify, to have a sort of a selection among the different constituents of the one which fits best with the target, and that is an adaptation to the presence of that target. Now, because of the name of this lecture, I chose some of the results which had to do with some kind of sugars. And mannose is a sugar, okay? Now, concatenamide is a tetrameric type of assembly where 4 proteins bind, each one binds trimannose, 3 mannoses, as shown here. This is the crystal structure. That's 1, 2, 3, 4 sides, and that is the trimannose. And so we thought, okay, let's see if we can test that. So this was a bigger system, 6 different sugars, of which one was mannose, and the other ones were other sugars, glucose, fructose, and so on. And we added here a group, benzaldehyde group, which can be detected by UV. And then also these connectors, which had NH2 groups, which can be 1, 2, or 3 of them in the same molecule. This gives now 690 constituents, so it gets more complicated. So of course there's a simple answer to that. You make a column where you attach some aniline, you let it run through, and the one which sticks on the column is the one which fits best. There's another way also of doing it, is what we call dynamic deconvolution. This means that you have a full library. You take one object out, then the library, because it's dynamic, will rearrange and generate all combinations except those which contain what you have taken out. That means you have made a sub-library. And then on this basis, you can see that if you have some kind of an observable, I don't want to go into details. If you have some kind of an observable, if what you take out has not much of an effect, then it's not important. If the one you take out changes what you can detect, then it is an important part. And here is the following. So that is the complete library here. That's the blank. Complete library, there is something happening. If you take out of this library 1, 2, 3, 4, 5, not much. 6 or big signal, it goes back to the blank. And then A, B, C, D, G, H, I. Those two are important. What are they? This one is mannose, and this one is 3. So maybe it's not the best one, but from this experiment, you know that mannose is best bound among all these sugars, and there are 3 of them. How they are connected, this is another affair, but that is at least this answer you can get. So it's a sort of a dynamic recognition and selection of a given carbohydrate and mannose, and there are 3 of those. Now, but it has been applied to other enzymes and other receptors, so I don't want to get into it, just to show you the demonstration of the principle. Now, what about materials? Materials based on reversible connections. We call those, if they are polymers, dynamic polymers. What are they? What can you do with them? First of all, people would have said it's stupid. You don't want the materials which are not strongly linked. But again, maybe something interesting can happen. So, if you now have monomers here, where you have a monomer with a spacer in the middle, and here 2 end groups which can connect by a chemical reaction, which is a reversible chemical reaction, with another monomer with 2 complementary functional groups, then you get a polymer where the connections between the monomers are reversible. Usually a polymer is made by cationic, radical, anionic polymerization, and this then gives static polymers. The links are strong. In this case, the links between the pieces, the monomers, are reversible. You can also make it on the supramolecular level, where this process relies on formation here of non-covalent interactions by molecular recognition, and you have interactional recognition, and you have functional recognition. So let's have first a look at what happens on the supramolecular level, supramolecular polymer chemistry. We introduced that idea, and I insist here on the date, you will see why not. In 1990, that was in my lab at the Collège de France in Paris. So the idea was, can we make polymers where the connection between the monomers is a result of non-covalent recognition type interactions? When we proposed that, polymer chemists didn't like it very much because obviously Staudinger had to battle a long time to convince chemists of his time that polymers could exist, big molecules could exist. Everybody was thinking that it was just aggregates. And he got his Nobel Prize because he demonstrated that macromolecules do exist. But here we come back to the fact that maybe we can make this breakable, reversible, not necessarily monomers, mixture of monomers, but things which can be dissociated and reassociated. So the first ones we made were the following ones. The spacer here is tartaric acid, which has two OHs which are derivatized by C12H25 units, C12H25. And at the end of this tartaric acid, on the carboxyl groups of tartaric acid, we introduced here a recognition group, a pyridine bis amide, donor of hydrogen bond, acceptor, donor. Okay. The complement to DAD is, of course, ADA, and this is the derivative of uracil, one of the nucleobases. So if you have a DAD and an ADA, you would expect those to be complementary and therefore form an interaction. So when you mix them, you expect to get a supramolecular chain where the cohesion comes from the formation of 3 hydrogen bonds to hold them together all along the chain. Without going into details, this is a solid, and that's a liquid crystal. So you can already see that the formation of this object leads to interesting properties which are not present in the components themselves. And this is a little micrograph that you see very nice fibers forming. First of all, let me just show you here a case where the assembly leads to sequential organization. There are 3 layers. These are the molecular components I just showed. These molecular components form then the supramolecular polymer chain, step number 1. But when you analyze the object you obtain, you see that it is not just a chain. In fact, you can analyze it and find that, in fact, it is a triple helix, which is going around the cylinder along an axis, wrapping around an axis, and the C12H25 units stick out. It's a sort of a hairy cylinder with lots of hairs. That's step number 2. But then because these hairs can entangle, they can stick together. And this is then step number 3, where you get these fibers, which I have already shown earlier. So these are 3 steps. From the components you get a strand. The strand, 3 of them wrap around an axis of a cylinder, and then they assemble. And you see here, in fact, this, the diameter of one of those stakes here is about this 40, 50 angstroms here. And you see they can run together and stick together and make these more complex fibers. Just to illustrate the 3-step assembly. This is sort of a self-organization which goes from the nanoscale to the micro scale, where these fibers have micro dimensions. Now, why did I say 1990? Because that's the year when we published the first paper in this field. But there was something else which was important. In 2013, I received an email from a small company saying that they had used supramolecular polymers for a biomedical application. They made some supramolecular polymers which were biocompatible, and they, in 2013, 23 years later of the first publication, they used it for fabricating cardiovascular implants for children who needed heart reconstruction because they had a very severe congenital cardiac malformation. And here is the first girl who got it. So Dominica, she looks very happy. She looks nice, huh? This was in 2013, and that's the surgeon who did the job. He was happy too. He looks happy. And this was done on October 23rd in Faculty Center for Cardiovascular Surgery in Moscow. There's Leo Kokiera. I met him once. He looks like this. He looks like a surgeon, a strong guy. Yeah? You have to be a strong person if you're a surgeon. And so there are more than 10 children are treated, And they also now developed in the same company, Celtis, also hard valves, because, okay, this is another application possible for this type of polymers. Of course, it's more complicated because the valve has to open and close, so there are other characteristics which are necessary, resistance and so on. But it was for us, of course, fantastically satisfactory that you could use these polymers and develop out of them materials for use in surgery. It also shows that it takes a long, long time. And when here, I don't think there are people with deep pockets sitting in the front row, but when there are people with deep financial pockets sitting in the front row, and tell them, look, without basic research, you don't have a result. It doesn't take very long. So be patient. They don't like that, to be patient. Another property which is interesting is materials which can disconnect and reconnect can also be self-healing. So this, just to illustrate that, I don't want to get into the details, it's published now. This is a film, you may see it's a very nice film because totally transparent. You cut it in two with scissors, you superimpose the two ends, and you press with your finger for a minute, and you can pull and sticks. So it's self-healing. This film is completely self-healing. You can pull on it and stick again, as it was almost the same as it was earlier. These are just the measurements. So this is supramolecular. Now let's look at molecular covalent dynamics. What do you have to do? Very simple. Any chemist will do that. Two carbonyl groups, two amines, and they make polyimines, polymers. Nothing special. And you can also make it with hydroxides and with aldehydes or ketones. So, what can you do with those? Suppose you make a film where A is a dialdehyde, B is a diamine. You make AB film, a polymer, and you can make a film out of it. Then you take another dialdehyde, A prime, and you mix it with B prime, another diamine. You get A prime, B prime, A prime, B prime, and so on. Now, what can you do? You superimpose them on top of one another. Since the bonds here are brittle, dynamic, reversible, you can now generate two combinations which do not exist at the beginning. The beginning of only AB, A prime, B prime. Now you can make A prime B and A B prime. And if one of those two new combinations has interesting properties, it will be there, it will appear. So let's take E as a reversible connection. And first of all, how can you change the dynamic properties of one of those films? Again, I simplify, I just give you the result. If you have this dihydroxide containing silicon, dimethyl siloxanes in the middle, which make it very floppy. The connection of this with this dialdehyde gives this very soft, stretchy, floppy film. Totally uninteresting for bit materials properties. This was done together with Mitsui Chemicals, who they were sending to my group co-workers, and they were very forward-looking. Then they were doing the basic chemistry in the group, and then the results, they were trying to see if they can use them for practical applications in Chiba in Japan. So, now you can consider hard, what might you call hard monomers. Monomers which are not so flexible. Of course, this is still flexible, but not as much as silicone derivatives. You add it, and they will introduce, because it's dynamic, the film can break apart and something new can get in. Now, since those things are harder, you expect that your mechanical properties will change. And indeed, when you introduce 25% of those ones, you get now a film which is still soft, but not as much as this, quite clearly. If you put 50%, you now have a film which is tough enough not to bend anymore under its own weight. And with 75%, you retain flexibility, but you have it even stronger. So that just shows that because you can introduce different entities into the preformed thing, starting with, you can get new mechanical properties. But more impressive is the fact that you can do that for optical properties. What do you do that? Again, you take two films, AB and A prime, B prime, and you superimpose it by a corner. At the place where it's superimposed, you can generate A, B prime, and A prime, B. Here. If one of those has some kind of optical property, like a color or fluorescence, you will obviously see it. So, my Japanese co-workers, they like this nice little objection. So, you have a head and ear. That's AB. You have the inside of the ears, the eyes, and the mustache, A prime, B prime. And then you read what you get, color, fluorescence. Where it's superimposed. So that just shows that indeed the recombination occurs, generating the other two possibilities, and we knew, because we had done, of course, separate studies, that one of them was colored and fluorescent. This one. So it's a sort of material which is responsive to heating, external stimuli. These other reactions are, I'd say, one of the emblematic reactions in chemistry. Because of time, I will be quick. We were looking for room temperature reversible disorder. All these other reactions are reversible if you heat enough. But of course, if you heat, that's maybe not what you want to do. So we were looking for one which is reversible at room temperature. And the combination of a full weight with dicyanoethylene is a very reversible reaction. At 25 degrees, it behaves like a chemical equilibrium. And then you have transformative debate, you have a cross-linking component, and you can then get. This is a film. For those who were in Strasbourg, you recognize this? The cathedral. And so you cleave it, you cut it in two, you superimpose the two ends, you press, and you can stretch and stitch it. So that is now a self-healing material, but on the basis of reversible covalent. The first one was on the basis of non-covalent. So you can extend that to biological systems. But I haven't time to do much about it, just to show you what can be done. First of all, you can make dynamic analogs of nucleobases. You can make dynamic peptoids. That means analogs of proteins where the connections are not are reversible between monomers. And also you can apply it to sugars. I will again show you an example of that because of the name of this lecture. I may say that all three have been tried. This here was done by Indian co-worker, Srinivasa Chari Nampali. This one was done by Anna Hirsch, who is now professor in Saarbrücken, and this one was the one I will show you in brief detail. So let me just show you a little bit about dynamic type of sugar or carbohydrates. You can make from using this hexaglucose, which is derived from cyclodextrin, by heating it. You can put at the end this unit, which has two hydrogens, and another disaccharide, where you have two aldehydes. You mix them, and you get then a rather long, big polymer, which has a bottle brush shape. It has been studied in detail by various techniques. And let me just show you then what it has as property. This, as you see here, with these side groups here, this dihydroxide and this diamine has a fluorescence which is blue. This is just cryo-10 microscopy news category. And this has been done, I haven't time to get into it. But what was interesting is that you can also use it to demonstrate the dynamics in this, the exchange possibilities. This A is the one which has a fluorescence blue. B here, where you have here introduced the carbazole, has a sort of dark green.
The one we introduce furan here, light green, the one we have a carbazole, and the furan, reddish. So this is just fluorescent properties. But if you now take the one which has a blue fluorescence here and add the unit which should lead to a green fluorescence, then you get a progressive transformation of the blue fluorescence into green fluorescence. That demonstrates that the system is dynamic. That's what I wanted to show at this stage. And that even also in the case of these derivatives of side chain sugars, we have dynamic systems. Main chain glycodynamos can be made if you have this dynamic aldehyde. This is of course protected here by O method, that you can deprotect it. Here you have a hydroxylamine derivative, alkoxylamine. This is a sugar unit. Now, if you deprotect, this will polymerize, and indeed, you then get a polymer, which is not a very big one, just 800 to 1000 by dosing, but it just shows that you can then generate this dynamic bond, which replaces the normal bond, which is forming the connections between the monomers. Just to show you that indeed it is dynamic. We take here this is a dihydrate of a dialdehyde. This is a bis hydroxylamine. This polymerizes to give a polymer of about 2000 molecular weight, and you can show that it is dynamic by adding this other hydroxylamine derivative, tertiary, and you get incorporation of this. In fact, you don't get you get a destruction of this by just replacing the oxime bond with this. Just to demonstrate that also in these glycodynamos you have exchange mechanism present. Okay, now, what about adaptive chemistry? That's the next step. What this means, adaptation? Adaptation means that the structure of the object changes in response to the environment, phase change, physical effectors, chemical effectors. Physical can be temperature, heat, photo, irradiation, and so on. And this, in fact, is a network. If you have a system of exchange compounds, they talk to each other, they form a network, because you do something to one of them. All the other ones will know that something has been done here. So what does it mean? What can it bring? First of all, let's see what we can do with dynamic systems, polymeric ones, and how they can adapt to the medium. Quite simply, carbazole with a chain which makes it hydrophilic. Carbazole itself is a hydrophobic core. Then you attach a chain which makes it water soluble. One of these components has two aldehyde groups, two carbonates, and the other one has two amines. So, you mix it together, and what you get? Of course, you get what we expect. A polymer, which has been studied in detail, where, because the system wants to minimize the contact with water, it wants to minimize the contact between the hydrophobic core and water. So it wraps around and forms a kind of rigid rod or helical size. This was demonstrated by various physical techniques. So, then, let me go back. Now you can, this is fine, the polymer is interesting, it has interesting properties, but that is not what I want to show. Let's ask a question to this system. We know that it polymerizes this way. Then we set it up in such a way that there is another compound added, so we have one equivalent, one equivalent, one equivalent. And now this has to choose between the other two. Either it generates a polymer which has only this and this unit, or it is that, or a random distribution. The result is to get the same as when this guy is not present. And this just sticks in solution and does nothing. It's not entering into the polymer. So that's point number one. You have the formation of the helical rod with a selective polymerization of the big ones, the one which have a larger hydrophobic core than this one, which has a smaller hydrophobic core. So since if you want then to demonstrate the hydrophobic effects will direct what the reactions, what happens to this dynamic system, you can now test it by adding acetonitrile to the water, converting progressively the pure aqueous medium to progressively more and more and more organic. And indeed, when you have added 80% acetonitrile, you have lost completely the selectivity, which is a good demonstration, a good indication that hydrophobic effects determine the outcome. So it's an adaptation to the medium. When it's pure water, it is only this one. When it's a mixture, right, of acetonitrile and water, at some stage it's less and less and less and less selective. So you have a selection of the components which then corresponds to the adaptation of the system to the environment. Another demonstration which is of interest is the following. We, together with Paolo Samori, my colleague who is doing nanochemistry, and using STM, EFM, or this kind of methods, we did the following. Take this long chain aldehyde. It was known that they deposits on the surface very nicely to form an organized structure. But then you can, of course, use this aldehyde and form imines on both ends of a diamine. It can be a short diamine, a longer one, or a longer one with 12 CH2 groups in phenyloctane solution. If you look at the NMR of that, you find that in the solution you obtain monoimines, only 1 to 5% bis imines, very small amount. Monoimines mostly, and monoimines of all three, C2, C6, B2, B6, and B12. And then you get the deposit on the surface, and you look with STM, what is deposited. And what you find is that it is only the bis imine of the C12, because that's the one which has the strongest absorption forces. So the fact that you have added now a possibility to deposit makes that the system is then directed by the forces of absorption to generating the compound which has bis 2 imines and which is a C12. Now, again here, there's something which is first of all interesting in terms of chemistry. The absorption drives the reaction to completion with the bis imines, and also drives component selection. Two things. The organization drives the reaction to completion, and it drives the selection for the right one. Now that is quite an interesting property. It's a surface absorption which directs, it's an adaptation to the absorption to the surface. It's a self-organization on the surface, and that can be quite interesting in the origin of life scenario. I come back to that, because just at this stage, I'm almost finished. At this stage, if molecules can change, if dynamic systems can change their structure as a function of how organized they are, that's a necessary step in the evolution of complexity. It's very difficult to imagine then complexity arises just because it's there. But there must be a process, thermodynamic process, which drives the system to get more organized and to select for what makes it more organized. Okay, so last paragraph. I told you all these things are networks. And let me just look into that, because I feel that's a very important property one has to analyze. Let's go back to AB, AB prime, A prime B, and A prime. These are four constituents which are generated by reaction of A prime, B, B prime, 2 by 2. A and A prime with B prime. That's a network. Very simple one. It's a square. You have these four constituents which form a square, and you can put them at the corners of the square. AB AB prime, A prime, B prime, A prime, B. You note that on the edges of the square, the constituents have a component in common. AB has one with A prime. AB has one with A prime B. So, if you do something to AB and make it increase, the other ones which share a component have to decrease. That's an antagonistic relationship. If AB increases for some reason, that decreases and that decreases because AB will be formed at the expense of AB prime, that A, and that B will give more AB. Okay. But on doing so, they liberate A prime and B prime. So A prime and B prime will increase when AB increases. That means it's an agonistic relationship. If two constituents do not share a component, if you increase one, its agonist must increase. And the important thing is it must, because A prime, B prime is liberated. So what does that mean? That you can modulate the constituents and that you have an adaptive network, because if something changes which makes one of those constituents change its percentage, all the other ones depend on that one too. So the whole system will have to reorganize. Let me just show that in an inorganic way. This inorganic way is just an illustration. It's very simple, but it's so simple, but it makes it understandable. Suppose you have this AB where you have A is pyridinaldehyde. It's trivial, in fact. And you have B, benzhydrazine. And you have then A prime B, the benzhydrazine, and A prime benzaldehyde. Here you have pyridinaldehyde and N-methyl benzhydrazine. And this, okay, these are the four. If you add the metal ion to this, what do you have? The metal ion will obviously bind very strongly to this one, because it has NO, 3 binding sites for a metal ion like zinc, for instance. If in addition you add a little bit of base, you will ionize the NH and make a very strong complex. So as a result of that, the system having 4 constituents will end up with only 2. One of these 2 is the one which can complex the midline, and the other one is its agonist. So this fellow, who doesn't do anything with the midline, nevertheless is increased in its proportion, it has a higher proportion, because the formation of this amplifies the agonist also. So you have amplification due to the binding of the midline. If you look at this in terms of the network, that's at the beginning more or less statistical distribution. If you add the midline, you have a very strong AB and very strong A prime, B prime. And you say, well, so what? So what? What is important is the following. That you have agonist amplification. In a system where you have agonists, if one changes in a given way, the other one has to do the same. If you have antagonists, they do the reverse. If one increases, the antagonist will go down, but the agonist will go up also. And this is quite interesting, because the amplification of the fittest for metal ion binding also amplifies the unfittest. This one which cannot bind metal ions. There's no way to bind. There's no good groups compared to the other one. So I think this is a very important property, that in a network, the fittest for a given, if I have to insist on that, for a given process, will also amplify in that set the ones which are the unfittest. That's also interesting for developmental biology, you will see just at the end. So let's have a look at that. Incidentally, the unfittest may have a color, for instance, which you cannot move directly. We have a case like that, where the unfittest for midline binding is colored, and not the one which binds the midline. So if you add zinc, it becomes colored. Not because the zinc is colored, but because the other guy, which is amplified, is colored. So that's now towards the end, almost. Conclusion still, but close to it. So, G quartets are well known. Supramolecular macroscientists, one can call them, where guanosine is forming a quartet, an organization where 4 of them are stabilized by a midline like potassium ion. And this is very well known. That is known for many, many years. They're also important in telomeres at the end of chromosomes, but I haven't found it. That's very known. Then you take your guanosine and the CH2OH here, you make out of it a hydrogen, CONH-NH2, so as to have an NH2. Okay. When you assemble that into this unit, which one knows is a very nice organized entity, this is the gel you get from that. It was known that guanosine itself made gels, so this is nothing very new. This was well known, had been studied by biophysicists for quite some time. But here the difference is simply that at the surrounding, at the periphery of this macrocycle, there are NH2 groups now. So what can you do? You can decorate it. You can decorate it by adding an aldehyde, so that the aldehyde will make here an imine at the outside of this macrocycle, this G quartet. Now, then we try and see by using different aldehydes, and we found out that with some aldehydes, it's sort of obvious, when you have negative charges in given conditions, the same conditions, if you add that aldehyde, the formation of the imine transforms the gel into a solution. Then there are other aldehydes, especially like pyridoxal, which is an interesting one also biologically, which when it forms the imine, forms a gel of higher melting point, that means a better organized gel. So that was interesting because introducing pyridoxal phosphate will increase the organization. You can you can understand that a higher organization leads to a higher melting point of the gel. So, what can you do then? First of all, you have to check that when there is no gel, there is no selection. And here, you see that if you don't have the guanosine derivative, but you have replaced it by an alanine, then you have 24 statistical distribution of the 4 constituents which can form. The same amount of all of that. No selection because there is no gel. And then you change your system. This is just to demonstrate, this is sort of a blank, so to say. And then you take, come on, now, you stick, sorry, okay, then you replace that, reintroduce in the system the one which can form a gel. And you expect the formation of 4 constituents. AB, AB prime, A prime, B prime, A prime, B. This is the one which does form the G quartet and therefore can in principle form a gel. And then you analyze. How do you analyze? Of course, the gel doesn't give an NMR signal, it's just very, very broad. But all the ones which are not in the gel give sharp signals, so you can analyze these, and by subtraction, you know that what remains is that. So what you obtain is the following. In the solution, you have only those. And as a consequence, in the gel, you have this. And here they are. The one in the gel, AB, is very high. It's amplified by gel formation. A prime, B prime, which is the agonist of AB, this one, is also very high because it has to be, because it's the agonist. And the antagonists are very low. And so this means again that amplification of AB, which forms the stronger gel than the starting one, this is selection under, so to say, the pressure of self-organization. When the system wants to self-organize, it wants to generate what makes it self-organized. I think that's quite a powerful thing. The system favors and generates what makes it better organized. And that, of course, has also to do with the same property we see about development of complex systems. Let me just show that, and then I will talk about, I think it's finished now. So, at the beginning, 4 constituents in the controlled step is about the same amount. Then you let the gel form, and you get this highly organized system where you amplify what is best organized, what is the best organization, also what is the least organized. And that is a selection under self-organization pressure. So at the beginning of this, self-organization pushes the system towards being more organized and generating the best organized one, and you get this. Incidentally, you may ask, okay, can you not just destroy the organization? Yes, you can. You melt your gel, and above the melting point, you go back to 25, 25, 20, not exactly, but almost 25, 25, 25. It's not exactly the same because the medium is not exactly the same. So if you just change the temperature, you heat, you cool, you heat, you cool, you go from amplification, no amplification, amplification, no amplification. And this is an adaptation again to the formation of the gel. So you have a selection under, I call that self-organization under pressure, that things want to get organized. And again, agonist amplification, the fittest amplifies also the unfittest. And this again, prebiotic evolution. You know, this gets a bit philosophical, I would say, but I'm convinced that our universe has the property to self-organize. If not, it would not exist. And you cannot make out of atoms directly a living organism. You must have steps between. And one of the basic processes is simply thermodynamics. Thermodynamics drives our universe. We are the result of thermodynamics, reversible and irreversible, and non-equilibrium thermodynamics. But this is the basic force which pushes in some regions of the universe to have more and more organized matter. Of course, because of entropy, some other regions become very disorganized, but that doesn't bother us. It's not our problem. So, okay, just to see, so what does it lead to? That this adaptation to selection is very important, and this is sort of a change of paradigm, that selection is important, and selection in dynamic system leads to the selection also, not only of the components, but of those which give the best organization, which can be of interest for materials and technologies. So, last picture. Let's have a look at the evolution of chemistry. We start with molecular. Without molecular chemistry, without knowing molecules, how to make them, how to design them, can't do the rest. But then you can build on that, making supramolecular entities where they get together, have new properties, interact with one another, they get organized. If they are dynamic, and if you have a dynamic, you get a higher step of complexity, they can become adaptive. Of course, later on, then they can be evolutive, that's more complicated. Because in evolution, not only do you have to adapt, but you have to keep what you have adapted with, and have another step. In this case, if you take away the effector, the one which makes the change, then you go back to thermodynamic equilibrium. So there's a lot to do still to make the system out of equilibrium and to see whether you can make the next step. In fact, there's a way to do it, which is you generate the first step, for instance with imines, you reduce the imine into amines, then they are not reversible anymore, and then you can hope to go further. I have a number of other things, but that's for next time when I come. So that's what I have to tell you about steps to complex maths. Thank you.